Okay, so drag is resistance to motion due to fluid flow. We represent drag force by the variable FD, and this force is due to a variety of factors. So there are many things that cause drag. The main thing that we think about is size and shape. Also, drag can be due to fluid viscosity. So that's particularly like you might have the same size object, but if you put it in air, it's a lot easier for it to travel than if you put it in water. So that's how fluid viscosity would play a difference. And then the size and shape, obviously a big object will have a larger drag than a small object. And then a shape that is smooth or has rounded edges will have a lot less drag than something that has sharp edges. Similarly to when fluid is flowing in a pipe, if you have a tight fitting or like a sudden bend in the pipe, then you're going to get a lot more drag and a lot more energy loss than if everything's just flowing down a straight pipe. So another thing that drag can be caused by is a wave, like a shock wave. So anything that is traveling at a high speed, like more than 200 miles per hour, will have the air will start to compress. And so you can get shock waves, especially if you're traveling faster than the speed of sound. So airplanes can experience shock waves because they travel pretty close to the speed of sound, like maybe 0.8 times speed of sound. But most vehicles are going to be pretty far below that. So typical speed of sound is about 700 miles per hour. Or about 330 meters per second. And this depends on the density of the air or the water. So sound actually travels faster through a thicker medium because it travels through vibration of molecules. So a sound will actually travel faster through a solid. Like if you hit a board and then it vibrates, then like the sound reaches the end of the board faster. Or like underneath the water, or even in more humid air, then sound will travel faster than it will in really dry air, because since the sound is due to molecule collisions, if the air is really thin, then there's not a lot of collision happening. And so then the last type of drag is lift. So this is particularly important in airplanes or jets or helicopters or things that fly through the air, because you want a component of the drag to lift the plane upwards. So if we look at something like airplane wing, so let's say here is your wing. That's probably not super great, but basically the top of the wing has to be more curved than the bottom, because the air comes in here and then you want it to go up over the top of the wing. And then it comes out here, and then this would go kind of more straight along the bottom. Because if the top of the wing is more curved, then the air has a longer path to go through. And so in order to keep the same mass flow rate, it goes faster. So air goes faster along the top than it does around the bottom. And that sort of creates a vacuum, like basically it's a low pressure, because high speed means low pressure. Okay, so that helps to lift the plane up. Now, also what helps to lift the plane up is the angle of attack. So let's say that your plane is pointed at some angle. Okay, so this first picture that we drew, this is like the side of the wing. This is more basically the angle that your plane is pointed at here. So we'll look at that and we'll say that here is the angle relative to the ground. So if the angle of attack is up, then the drag force comes in here. And this force is going to be at an angle to the plane. So if we draw angle of attack of the plane, and then we have the force. So we'll say here is the drag force, and there is the plane. Well, there's going to be some component of the drag force that is perpendicular to the plane. And this component is the lift. So at first, as you tilt the plane backwards, then you get more and more lift. Well, at some point, you're tilted up too far and the plane's going to stall, so that's not helpful. But basically, you do want to be at some angle between flat and between vertical. And typical is about like 19 degrees is where you get your peak lift coefficient. So if we have this x-axis, and we'll say that here on the x-axis is angle of attack, that angle, and then here on the y-axis is the lift coefficient, CL. Then we kind of get something that goes like that. Okay, so at some point you're not going to get lift anymore. This is at 19 degrees. And peak lift coefficient is usually around 1.6. Lift coefficient has no units. And then this crossing point is about 0.2. And then the midpoint here, this is about 10 degrees. And we have about 0.9. So this is based on information from NASA's website is where all that came from. But basically the point is that tilt your airplane up a little bit, you get more lift. Tilt it too far, you stall. Tilt it really far and you flip over, but hopefully nobody does that. So that's the lift coefficient. Now, just a little digression on more about airplane wing shape. So NASA's got this simulator here. So this white slug represents the side of the airplane wing. And you can see here the flow of the wind. And if you slide this little bar, you can change the wing shape. So if we move the slider bar one direction, we can see that the wing is curving that way. And so based on these flow vectors, we can see that it takes, the air has to go faster. We can see the sort of steeper velocity vectors over the top than it does on the bottom. And over here, we get a positive lift. Now, if we tilt the wing the other direction, so we go back here to 0, we basically get no lift. And then if we go the other direction, you can see that's bad. You would get negative lift. And so basically the air would be forcing you onto the ground. You wouldn't be able to take off if your wing was put on the plane upside down or, just had larger surface area on the bottom than it did on the top. So back here now to talk about drag. So the drag coefficient is known as CD. So that drag coefficient is based on the size and shape, like the features of the object. Really, this drag coefficient is really a property of the vehicle. And that's kind of what they're measuring through the wind tunnel. So you want to make the drag coefficient as low as possible if you want to reduce your wind resistance. So like a race car would have a really low drag coefficient compared to, say, a bus, because there's a lot more money going in the race cars than the buses, and the race cars need to be fast. So drag coefficients, you can look them up in a table, sort of like coefficient of friction. But some typical ones here, so we would have like 0.6 to 1.0 would be for a truck or a bus. Something like an airplane wing would be 0.15. a car would be like 0.2 to 0.3. And a person is usually around 1.0. But a person on a motorcycle is way worse than that, 1.8. So these are just some common ones. If you're trying to find it for a particular object, then you can look it up in the table or you can find it experimentally. And that's why we have these ranges, because obviously not every car is made the same. Not every bus is made the same. And so there's just kind of a range there. So we can do some drag calculations now. So the formula that we're going to use, formula for drag force, is 1/2 rho CD V squared A. So we'll go through what each of these are. Now, CD is the drag coefficient. We just talked about that over here. So the total drag force depends on the drag coefficient as well as some of these other factors. So rho is the fluid density. So for air, it is about 1.225 kilograms per meter cubed. And this obviously is going to depend on your altitude and your humidity and all of that, but this is just sort of an average value. Rho for water is about 1,000. And it's less in freshwater, more in saltwater. So saltwater is a little bit denser and more buoyant. But these are probably the two most common ones that you're going to use. Now, V is velocity. So this is relative velocity of the fluid and the object. So for example, if the air is still and the car is moving, V is going to be velocity of the car. If the car is still and the air is blowing, then V is going to be velocity of the wind. But if they're both moving, then you have to add them together. And the way to think about that is basically will it make the drag force higher or lower? So if you have a vehicle moving with, we'll say, V car, and then you have the wind blowing against it with, say, V wind, then the total V is the two magnitudes added together. So remember that the signs, if you're talking about vectors, the signs are going to be different because they're going in opposite directions. But what you want here is a total magnitude if you've got a headwind like that. Now, if you've got a tailwind, then obviously that's going to subtract. So if you have the V car like that, and then you've got a tailwind, then the velocity, you would subtract those. And so this distance would be your final V, because the tailwind pushes you along, so there's less difference between your speed and the wind speed and less drag force that you experience from the front. Whereas if the wind's blowing against you, it's really, really hard. So that is V for velocity. And then finally, A is the frontal area. So this is the two-dimensional area that the wind sees. Whatever direction you're going, what area is perpendicular to that direction. So if a car is driving, it is the front of the car. We can say that drag force is negative because it is sort of like friction. It always goes against you. So magnitude of drag force is positive, but the direction is in reverse of the motion. And so that's why we would put a negative sign there. Now the area, you can typically approximate these as standard shapes. So like the front of your vehicle is a box, then make it a rectangle. If you have something like a go-kart, so you've got a go-kart, sort of looks like that. So you might want to approximate that one as a triangle. If you have a truck, it's like a box, it's a square. So basically, even though you have the front of the vehicle, and so like the part here where the lights are, is going to be closer front to you than the windshield. We're just looking at the two-dimensional area to get that A. So the area, the speed, the drag coefficient, which is going to be mostly based on the shape, and the velocity of the fluid all go into drag force.